This video demonstrates how Geogebra can be used in the context of a linear programming problem having only two decision variables. There are 5 main steps in the process. First, we work from a mathematical formulation of the problem. Then, referring to that formulation, we use Geogebra to graph the constraints. Next, we use Geogebra to create a slider to control the value of the profit P. Then we define the objective function in terms of the decision variables and P. Finally, we create a slider to control the value of F, the profit margin, on one of the skateboards. This is the formulation of the problem from the ATM article. It defines the decision variables and also defines the objective function and the constraints in terms of the decision variables. The first step in using Geogebra to graph the constraints is to rescale the coordinate system, similar to what one does with the viewing window in a graphics calculator, so that the graphs will be visible. To do that, we click on the button that appears to show the coordinate axes. Clicking on the small triangle at the lower right of the button brings up a menu. Select Zoom Out and click on the graph displayed in the Geogebra window until the units on both axes are scaled in units of 50, 50, 100, 150, and so on. Then click one more time. Go back to the Coordinate Axes button, click on the small triangle to bring up the menu, and click on Move Graphics View. Now click anywhere in the graph and drag until you can see 0 to 450 on the x-axis and 0 to 350 on the y-axis. You may have to resize the window in order to see all of this. In order to graph the constraint inequalities, we graph the associated equations. 5x plus 15y equals 2,250, and 7x plus 10y equals 2,250. To do so, click on the white bar labeled Input that runs along the bottom of the Geogebra window. Now type in one of the equations. Press Enter. The line appears in the coordinate system, and its equation appears in the algebra portion of the window under the heading Line. Then repeat the process to enter the second constraint equation. When you type in the equation 5x plus 15y equals 2,250, because there is a common factor of 5 in each term of the equation, Geogebra will automatically simplify the equation to x plus 3y equals 450. Notice that the non-negativity constraints are already represented as the coordinate axes. Now we label the corner points of the feasible region. These are just the points where the constraint equations intersect. To label the origin, simply type O equals, open parentheses, 0, 0, close parentheses, into the input box, and press Return. To label the other 3, we will use the Point button, which is the second from the left. Clicking on the small triangle at the lower right on the button again brings up a menu. Select Intersect two objects, then click on the y-axis and the line x plus 3y equals 450. The point of intersection will be labeled. Repeat by clicking on the lines x plus 3y equals 450 and 7x plus 10y equals 2,250, then 7x plus 10y equals 2,250 and the x-axis. The remaining 2 corner points will be labeled. Finally, we use the polygon button to shade the feasible region. The polygon button has a triangle on it and is 4th from the left. Click on the menu triangle and choose Polygon. Now follow the directions on the screen by clicking on each corner point of the feasible region. Be sure to finish the process by returning to and clicking on the corner point you started from. At this point, we will create a slider to control the value of P. First, locate the slider button marked with A equals 2, second from the right. Click on the menu triangle and choose Slider. Now move the cursor to the approximate location where you would like the slider to be and click. A slider dialog box appears. Click inside the white triangle below Name and type in an uppercase letter P, the name of the variable whose values will be controlled by the slider. Next, fill in the 3 smaller rectangles with min 0, max 7,000, increment 100. This defines P in an appropriate range beginning at 0 and changing in steps of 100 through 7,000. Click on Apply and a line segment labeled P equals 1 will appear. Notice that the line segment has a point marked on it. Click and drag the point. Notice that the point slides along the line segment, and as it moves, the value displayed for P changes. Our next task is to define the objective function in the input box. Recall the input box runs along the bottom of the Geogebra window. Click anywhere inside it and type P equals 15x plus 35y. When you hit Enter or Return, the equation 3x plus 7y equals some number will appear. Geogebra has automatically divided out a common factor of 5 from the 2 coefficients, and 5 times the number on the right side of the equation should equal the number currently displayed by the slider. There is also a new line displayed in the graph. Drag the slider point back and forth and notice that the line appears to move as the value of P changes. Drag the slider point to the right and watch the value of P increase as the profit line moves towards the top right of the feasible region. The last point in the feasible region that the moving line touches must be a corner point, and that corner point represents the optimal solution. The last thing we are going to do is create a slider to control the profit margin on the fancy skateboards. This will allow us to investigate the sensitivity of our optimal solution to changes in the value of F. We create this slider using the same steps as we did to create a slider for P. Name this second slider uppercase F and assign the following values: min 20, max 60, increment 1. Now click on Apply. The new slider appears. Next, delete the old profit equation and replace it with a new one that uses F. Under Algebra, in the line section, highlight the equation representing the profit, which should be the third in the list, and delete it. Now, in the small input window, type and enter 15x plus uppercase Fy equals P. a new profit equation appears in the line section and a new line shows in the graph. Click on the movable point on the slider and drag it until the slider displays F equals 35. This recreates the graph of the given problem formulation. If necessary, drag the slider for P until P equals 5,900 is displayed. The profit line should appear to pass through point B on the graph. Now click on the F slider and drag the point until it displays F equals 20. The optimal corner point is now point C, which can be confirmed by dragging the profit slider point. Finally, drag the fancy slider until F equals 45 is displayed. Notice that the profit line now appears to be parallel to side AB of the feasible region. This can be confirmed by checking the slope of each line.